The role of corporate finance is shifting. It is moving from logging what already happened to predicting what will happen and automating the steps in between. But many finance departments stumble during this transition. Instead of engineering a cohesive system, they buy fragmented, ad hoc software patches. Over time, these disconnected tools collapse under their own weight. To actually achieve this transformation, an organization has to build a rigorous, 5-stage analytical pipeline. The foundational architecture used to construct this pipeline is the Systems Development Lifecycle, or SDLC. Long before a single line of code is written or a vendor contract is signed, the SDLC forces a rigid organizational needs assessment to define exactly which goals are currently unmet. Piecemeal software adoption isolates data into dead-end silos. The SDLC approach engineers a unified engine designed from the ground up to predict future outcomes. This diagram maps the 7-phase systems development lifecycle. It dictates everything from initial project feasibility through operations and maintenance. Down in Phase 4, the building and development stage, the tech stack is chosen and infrastructure assembled. The lowest cognitive tier implemented here is robotic process automation, or RPA. Organizations deploy RPA bots strictly for rules-based, highly repetitive tasks, like processing thousands of vendor invoices. While an RPA bot strictly follows fixed instructions, artificial intelligence and smart machines operate differently. They attempt to imitate human decision-making, adapting their behavior and generalizing concepts based on past experience. Another layer of the stack might incorporate blockchain technology. This acts as a decentralized public digital ledger that relies on a consensus mechanism among multiple independent entities, entirely removing the need for a central administrator. When organizations deploy smart contracts onto these blockchains, the code must be deterministic. That means a specific input will always yield the exact same output, ensuring terms execute automatically without exceptions. Whether an organization deploys a basic RPA bot or a complex neural network, the entire tech stack is essentially empty plumbing. Its strategic value depends entirely on the quality of the data flowing through it. This graphic illustrates the 4 V's of big data. Volume refers to the massive scale of information captured continuously. Variety covers the wide mix of file types, from structured SQL to unstructured media. Velocity represents processing speed, and veracity measures data trustworthiness. In its raw state, big data inherently lacks veracity. It is filled with useless information, duplications, and errors, commonly referred to as noise. To fix this, data engineers build an ETL pipeline: extract, transform, and load. This mechanism pulls raw data from multiple sources and refines it into a uniform format. Within the ETL process, data normalization strips out duplicate entries and structures the remaining elements as efficiently as possible. This strengthens data integrity for specific analytic purposes. If the ETL process fails to clean incoming data, veracity drops to 0. Consequently, downstream predictive models will process that noise and confidently output toxic strategic advice. Once the data is clean, the organization moves up the analytics maturity curve. The analysis shifts from describing what happened in the past to predicting what will happen next. Regression analysis is the primary predictive method used here. It derives an equation mapping the linear relationship between variables. Simple regression tests exactly one independent variable against an outcome. Multiple regression weighs several independent variables, like advertising spend and price, on an overall result.
The accuracy of this fit is measured by the coefficient of determination, or R-squared. Analysts also calculate the standard error. This is the vertical distance between the actual plotted data points and the projected regression line. The closer the points to the line, the lower the error. There is a critical limitation to this modeling. The linear relationship established is only mathematically valid across the relevant range, the span between highest and lowest measures in the historical data. Outputs outside this range become highly unreliable. Furthermore, regression only maps correlation. Even if 2 variables move together perfectly, the math cannot prove an underlying causality between them. Regression analysis provides the mathematical probability of a future event occurring. Human finance executives must still apply their judgment to determine why the variables are linked in the real world.
To project trends based on past experience, organizations use time series analysis, a regression model where the independent variable is strictly time. Data can exhibit a seasonal pattern, fluctuating reliably over a fixed period. This contrasts with a cyclical pattern. Cyclical rises and falls happen over multiple years without a fixed, predictable duration, like broader macroeconomic business cycles. The model will also capture irregular patterns. These represent random, unplanned events, like a sudden weather anomaly, that statistical models simply cannot foresee. The primary limitation of time series analysis is that the historical components driving past fluctuations can become less reliable over time, leading to misleading conclusions. By isolating these temporal patterns, time series analysis allows finance departments to predict exactly when capital will be needed, enabling proactive resource allocation instead of reactive scrambling. The final stage of data analytics lifecycle is communication. The computer systems calculating the regression models do not need visual charts to make decisions, but human managers do. This is a statistical control chart. It is deployed specifically to monitor a repeated manufacturing or operational process to ensure the output stays within acceptable upper and lower control limits. For quality control analysis, managers rely on tools like this Pareto diagram. By arranging data from highest frequency to lowest, it quickly isolates the largest sources of operational errors. When the goal is to illustrate the correlation between two distinct variables, analysts deploy a scatter plot, using horizontal and vertical axes to map individual data points. A bubble chart takes that scatter plot foundation and incorporates a third variable. The physical size or diameter of the data point itself communicates additional quantitative information. Selecting an inappropriate chart type obscures the mathematical truth of the data. Poor visual communication neutralizes all the intensive computational work executed in the prior pipeline stages. Visualization tools can easily be manipulated to present a biased picture. By zooming in on a minute variance and cutting off the y-axis zero baseline, a flat line of expenses can visually distort into a false narrative of extreme volatility. Maintaining visual integrity requires strict rules. Always start the axis at zero, display the underlying calculations, and limit colors to prevent overload. Achieving a true technology-enabled finance transformation means abandoning ad hoc software patches. It requires engineering a unified pipeline where high-veracity data flows frictionlessly into predictive models. By mastering this life cycle, the modern finance professional stops functioning as a backward-looking bookkeeper. They evolve into the architect of the organization's strategic future.